And welcome to today's seminar. Today's speaker conducts research at the nexus of mind-motor-machine interactions to understand, quantify, and predict human performance and health indicators in high-risk environments. She is an associate professor in the Department of Industrial and Systems Engineering at Texas A&M and a director of the Neuroergonomics Lab. Her research on understanding and mitigating fatigue and stress-related variability in worker health and performance has been funded by many federal agencies, including NIH, NSF, and NIOSH. She is an elected Executive Council member of the Human Factors and Ergonomic Society, HFES, and chair of the HFE Woman Group at HFES. Please help me welcome Dr. Ranjana Mehta.
Thank you, Joseph. I really appreciate it. And thank you everyone for coming in on an afternoon. I will not talk about fatigue as much because I don't want to fatigue you all too much with my talk on it. But what I'm going to do is talk about neuroergonomics as an emerging science to understand the intersections of humans and systems interaction. So feel free to, chime in if you have any questions while I'm going through. I would love for this session to be interactive. Or if you prefer, you can always, ask a question in the chat and I'll try to multitask. So as Joseph mentioned, I'm an associate professor in industrial systems engineering at Texas A&M University. My research is at the intersection of mind, motor, and machine interactions. The goal of my lab is to understand mechanistically, assess feasibly with relative fieldability, and augment human capabilities in high-risk environments. Some of the recent thrusts in my lab have been in emergency response and in offshore oil and gas work. So when we talk about how humans interact with systems, there are a lot of different groups, even in human factors. We call them neck up. There are folks who look at the cognitive engineering components, and then we have the neck down folks who are the biomechanists and the ergonomists who look at how anthropometry, muscle fatigue, work physiology can impact a worker's interaction with system. My research focuses on the interplay of these two factors. And in doing so, we take a very integrative approach. We understand what's happening in the brain, and we sort of document using various cognitive techniques what's happening in the mind. We also use a lot of autonomic and peripheral sensing systems to understand what's happening from the cardiovascular perspective, from the neuromuscular perspective. So we have used heart rate variability. We have used electromyography to look at muscle activity, and we've looked at tissue oxygenation to look at, blood flow dynamics in the muscles. And then we also move on to the sort of end effector. How does this mind-motor machine interactions impact movement kinematics or human behavior? So, how is a person sitting? Are they slouching? When they are stressed, fatigued? How they walk, does the gait pattern change? Whether we can identify based on a person's tremor features if they are going through certain state changes such as stress or fatigue, and then looking at general movement variability. So we have a lot of different research interests. Largely, we have research interests in the mechanistic and the applied domains. In the mechanistic domain, the Neuroergonomics Lab focuses on neuromuscular fatigue. When you think about muscle fatigue, a traditional approach is you look at what's happening in the muscle. But really, signals are sent from the brain. And so my research focuses on mind-motor interplay, where we look at how and why individuals get fatigued the way they do. And we have extended this work in older adults, individuals who are obese, and individuals who have certain chronic conditions, both physical and cognitive, such as diabetes as well as depression. This has been funded by NIH and NIOSH. We then sort of, these mechanistic studies help us in understanding what sort of approach needs to be taken in order to do applied research. And a lot of our applied research has been in the oil and gas domain, where we have looked at predictive health and safety in offshore oil and gas workers. So we are trying to understand fatigue, causes and consequences in this domain. And while, my personal interest has always been to understand what's happening to the human brain and mind as well as body, we have realized doing research in this domain that sometimes we have to adopt techniques that we are not comfortable with. So for example, as an engineer, I love quantitative data and I loved brain imaging, but I had to settle for surveys as one of our primary ways of collecting data in the field. So there's a lot of compromises you make as a researcher, but you really understand the importance of working in very different domains that have different constraints. And finally, one of the more recent thrusts of my lab has been in understanding human-robotic interactions. That is going to be the focus of this discussion. And lately, we have been moving towards human automation interactions, understanding autonomy, the science of autonomy. And this has been funded by NSF largely. So if I want to use a neuroergonomic approach, which is understanding the brain at work, I need to be able to choose a right neuroimaging technique for the sort of work that I do. My work is understanding physical capabilities of humans that may get impacted by cognitive underpinnings. And so the sort of techniques that I need to utilize in my lab need to be non-invasive. They need to be low cost and they need to be transportable. That means they need to be ambulatory. They also need to be movement friendly. So any technique that I have will need to be robust against motion artifacts. Finally, some of my work is mechanistic in nature. So I would like for the neuroimaging technique to sort of tell me what regions of the brain fire up rather than whether signals cross that regions of the brain. So I need the technique to help me in understanding mechanisms. And I need the technique to also be compatible with other modalities, because more and more, as and when people get familiar with the field of human factors, we realize that just one set of data that comes from the human is an incomplete picture, because we ourselves have five senses. We utilize a lot of different modalities and we sort of make decisions and perceptions about the environment around us. Similarly, if we have to understand human behavior, we need to look at a lot of different modalities. And so, this was this was a process that I went through when I started my tenure track position a long time ago. And I realized functional near-infrared spectroscopy. This is a very emerging neuroimaging technique that's highly ambulatory. And I'll show you a lot of data from this technique that provides me the sort of like a sweet spot in terms of temporal resolution. It's a neuroimaging technique that looks at how neurons fire and how blood oxygenation is impacted in the area that neurons are getting fired. So it has relatively low temporal resolution compared to, let's say, an EEG headset, which is sort of what most people know what neuroimaging is. It's, you have a lot of electrodes on your head and it measures electrical changes, impulses that flow through different regions of your brain. But it also gives me a good sort of spatial resolution. It's decent, it's not the best. So an fMRI going into a scanner would have been a perfect system, but I can't really take an fMRI scanner out onto our RELIS campus and fly drones. And then so, we need something to be ambulatory. And it also provides, the most important thing is it provides a high level of movability. And that helps us with doing, applied research that can be translated to, workforce research right now. The advantages of neuroergonomics to other imaging or other modalities, such as, let's say, heart rate variability. So, a lot of focus has been in the literature has been on these wearable sensors that are wrist worn, chest worn, that basically get you beat to beat data of how your heart is functioning that can tell you something about what's happening to the person. And it has been used to identify PTSD, detect PTSD triggers, stress and anxiety and whatnot. There are some challenges with such techniques in that they provide us with one temporally dynamic curve. Now you can get some idea of what's happening to the human during this time, but you really can't disassociate that the changes in this signal is due to, let's say, trust versus anxiety or anxiety versus fatigue. You can't distinguish it because it doesn't give you a spatial richness. So this dimension, this modality is not multidimensional. comparatively, any sort of neuroergonomic technique, and in my case, functional near-infrared spectroscopy or FNIRS, gives you, for each of the electrodes that you are looking into, it gives you a temporal curve for that, where it tells you time-dependent information, and you can also spatially know what regions fired up versus not. This is important because we know that neuroscience has been an established science for a long time, and we know there are certain regions of the brain that regulate certain behavior. So for example, we know that the frontal lobe is associated with decision making, judgment, it is associated with working memory, certain capabilities of humans. And if those regions fire when someone is doing a task, or if they fire too much, or if they don't fire at all after doing the task for a long time, we will know something has happened. And because we have the spatial resolution, we are able to sort of get some mechanistic understanding of how and why different experiences of humans reflect on this probe map. We can go a step further, which is what I'm doing in my lab right now. 3 of my students are operations research students who have expertise in graph theory and network analysis, where this is a highly multidimensional data set for them. And they are using this data set to understand causal pathways or networks of regions of the brain that get engaged or disengaged as a person goes through certain experiences or certain states. So I'll talk a little bit about that too. And then the one thing I wanted to highlight in my presentation is I'm not an expert in everything that I talk about. There is some value to collaboration and convergence across a lot of different domains, and you will see that reflected in the sort of topics that my lab has taken up recently. I'm going to focus on human-robot interactions because this is where much of my work in the past 3 years have been. If you think of robots to help, they could be remote or teleoperated, they could be collaborative, where humans and robots share the same physical space, or they could be wearable, such as exoskeletons. Across all these 3 different experiences of human-robot interactions, there are certain constructs that we as human factors folks need to understand and document and quantify, such that human-robot interactions can be more effective and more productive. We need to quantify the performance of the human when human is working in a team. So you can imagine how difficult that might be when we grade our course projects. We sort of get peer evaluation for with our students who are working with each other, and it's relatively difficult to understand who is doing what work. Similarly, in a human-robot team, how to quantify human performance when robot takes away some of this responsibility or maybe even autonomy is something that is still up for still not understood as well. So that's something that we are trying to look into. We also wanted to know how can we augment human cognition when workers, particularly emergency responders, are interacting with these new technologies in an off-normal situation. One of my students actually was deployed to Hawaii when the volcano erupted because we were interested in quantifying fatigue and the UAS pilots who were public safety UAS pilots who were flying continuous 4 or 5 days, trying to see where the lava was flowing so that information could be sent back to public safety officials so that maps could be updated and the community and the public could know, where to go and where not to go. And so identifying what are some of the limitations in humans interacting with these small UAS is important, because that is when we can sort of create solutions for them to perform adequately. At the very minimum, we want to make sure that the collaborative or the remote teleoperated or the wearable robotic doesn't increase physical cognitive burden, right? So anytime you have an intervention on a solution to solve one thing, you may create another new risk. And so that is also a focus of our research, is to understand whether there are new emerging risks that are being created. We want to look at fluency between the human and the robot. We want to make sure that they are very fluent and the communication between the human and the robot is relatively smooth. And trust is an example of that. So there is this whole thrust in our lab that's looking at human-robot trust. I'll touch upon that very briefly to showcase where we are going with it. And finally, training on a new technology takes time. So how can we develop robotic systems that have learnability components in them, that are designed such that humans can quickly learn them? So that has also been another focus of our lab. So I'll talk about exoskeletons specifically in this presentation, because this is something that has matured in our lab relatively well compared to some of the other work. So exoskeletons, both active and passive, powered exoskeletons as well as passive exoskeletons have seen a huge growth in the US industry. Passive exoskeletons have been there for some time with rehabilitation and in the military domains, but active exoskeletons, but passive has shown a huge, there has been a huge adoption in the automotive industry. Sometime back, I just heard that Boeing may have all of their workers wearing exoskeletons. Now, passive exoskeletons is a relatively new tool in the industrial domain, and there has been some work done on it, but we don't know the entire implication of someone wearing an exoskeleton, because even the design of exoskeletons industrial exoskeletons have been slow compared to its adoption in the industry. So if we want to evaluate how human exoskeleton interactions occur, whether they are good, whether they are bad, whether they need to calibrate over time, we need to have a framework for this evaluation. And we borrowed a framework from Boff in 2006 that looks at different fits of humans to technology. The first, simple fit that everyone thinks about is physical fit. You may think of that with respect to anthropometry. So how big of a device we need to design, how heavy it needs to be, and all of those things. So in the exoskeleton evaluation domain, this physical fit has been extensively studied in the past 3 years. And there is consensus in the literature that talks about that passive exoskeletons are able to reduce spine compression forces and back muscle activation, which means that they have been able to reduce load on the worker's spine so that they are at less risk of injury. And studies have shown consensus in that if you wear a passive exoskeleton, that energy expenditure of the worker is relatively lower than when you're not wearing an exoskeleton. So that's great. However, there are some emerging risks. An exoskeleton that's worn for the shoulder, a passive exo that is worn for the shoulder, may reduce the loads at the shoulder, but that load needs to go somewhere and it gets transferred to the back. And that may not be good in the long run. However, no studies have really looked at longitudinal impact of shoulder exoskeletons on back spine forces. And there are some mixed results on lumbar spine loading based on exoskeletons that are not of the back, but of, let's say, the shoulder, of the hip, of the ankle. The next generation of human exoskeleton evaluation could be thought as cognitive fit. So once we go beyond the physical fit, we then talk about, okay, so how easy is the system to use? Or, is it confusing? Are you able to do it the way it has been designed? So those are some of the ways in which, evaluations for technology would go into the cognitive fit. For exoskeleton studies, there have been very limited number of studies that have looked at the cognitive fit of exoskeletons. And they have found that exoskeletons increase workers' perception of workload through a subjective questionnaire. And through a cognitive dual task paradigm, which is an established paradigm in cognitive engineering, the study has shown that when a person is wearing an exoskeleton versus not, their vigilance their vigilant demands increases during a dual search task versus not. So there are negative implications of wearing an exoskeleton on your cognitive capabilities. Now, there are some challenges to this framework, the cognitive fit framework, because right now we don't have tools that can assess the cognitive fit. So for example, we have a survey that the person does all the lifting, and at the end we ask them, what was your perceived workload? A lot of people, are not able to reliably provide the responses to that, unless it's really high, right? Or it's really low. The second thing is, if you have a cognitive dual task while you're lifting boxes, a worker may not necessarily be doing this at their work. And so a cognitive dual task experimental paradigm is relatively intrusive and invasive to the task itself. What we really need here is a tool that can continuously, without interrupting the operator, quantify the cognitive fit of the exoskeleton as the user is lifting boxes or doing some physical task. This is where neuroergonomics can help with the neural fit. I believe that neuroergonomics can play a huge role in at least three things that we need to do right now. One, we need to identify the control systems in our brain that are recruited during human exoskeleton interaction. I will, if you're wearing an exoskeleton and you're doing a task, you will need to get used to it, right? And if you need to get used to it, that means you need to forget the motor models that you have developed over the years, let's say lifting boxes. And you can't rely on them anymore because all of your proprioception, your joint kinematics are changing as you are using the exoskeleton to lift. So your brain is redeveloping or rewiring its motor models. And because of that, we need to understand the control systems in the brain. So what regions of the brain get engaged, disengaged, overly engaged during human exoskeleton interaction. We can also use neuroergonomics to quantify the cost of the physical fit. So yes, let's say if an exoskeleton is helpful in reducing spinal pressure, at what cost? Does it increase your neural resources to do the same tasks that you wouldn't have to recruit if you weren't using the exoskeleton? And what is the trade-off? Would you rather recruit more regions of the brain, or would you rather have 10 newtons more pressure on your spine? And the research is completely unexplored in this domain. And finally, as we see in the rehabilitation domain, where we have powered exoskeletons that have, that can be programmed and can have autonomy and have a mind of their own, industrial exoskeleton companies are seeing that vision for industrial exos in the workplace. So if an industrial exoskeleton that a worker is wearing may potentially have somewhat, some level of autonomy, we need to develop an intellectually coupled human exoskeleton system, some sort of brain-machine interface that will help the human and the exoskeleton to talk to each other. If we use more, muscle activity or movement as the language with which humans and exoskeletons interact, that's really late, because that is sort of like the end behavior of the human. We really need to go towards the brain to get, the message across sooner, such that the movement between the human and the interaction is fluent between the human and the exoskeleton. All right, so so far I've talked about some of the potential ways in which neuroergonomics can help understand human exoskeleton interaction. Here is our our initial study that we looked at in collaboration with Ohio State University, Dr. Bill Maris with the Spine Research Institute. So, these folks at Ohio State, I was going to say OSU, but we may get confused. But folks at Ohio State are experts in biomechanical evaluation of spinal loads under, working conditions. So you can see over here that we have, kinematic information through motion capture. We have force plates that a participant is standing on, and they have an EMG assisted model that they use to identify low back spinal forces, both compression and shear forces. What we did is, me and my student went there, we stayed there for a couple of months, and we actually collected this data. The task really was very simple. People had to come into the lab and they had to lift in a very paced manner at 6 lifts per minute for 30 straight minutes. And this was paced using a metronome. And they lifted a weight of 7.25 kg. And the number of people that we collected the data was on 12 healthy participants. We had We gender balanced them. So we had male and equal number of male and female participants. And the exoskeleton we used over here was a Leber exoskeleton. So that's one of the limitations of the study, is that we only had one exoskeleton. Participant came on different days. One day they came in and they did the same task. They did this physical task without an exo after certain training. And then they came in on a separate day and they were equipped with their exoskeleton. They got familiarized, they could move around, and then they did the same task with an exoskeleton. The order of whether they got the exoskeleton first or the control first was counterbalanced between the participants. These are some of the measures. I talked very quickly about what Ohio State collects. So they have, EMG, kinematics, anthropometric, kinetic force, and moment to look at biomechanical performance parameters, which are essentially your moment at your L3, L4, and L5, S1 of your spine, as well as compression and shear forces at these locations. What we collected was the participants wore a functional near-infrared spectroscopy the whole time. And we got the FNIRS data from three major regions of the brain. One was the supplementary motor area, one is the premotor cortex, and one is the prefrontal cortex. And we did analysis, I'll talk about what those analyses are, to look at the neurocognitive demand. We wanted to first do a simple ergonomic assessment, which is look at the biomechanical data, which is what the current literature is doing. We did find a positive effect of the exoskeleton on spine compression shear forces. Ideally, the exoskeleton should have reduced spinal compression forces. We found a trend, but these were not significant. We did find that the exoskeleton significantly reduced shear forces. So these are forces perpendicular to the spine at the L5S1, which is a critical joint for and has been implicated a lot of times in low back pain. However, this decrease may not be considered practically significant. This is what we did with the FNIRS data. So we wanted to look at what regions of the brain were getting engaged and remaining engaged and contributing to the task at hand. So we tried to develop the neuromotor control network associated with human exoskeleton interaction. So if you can imagine, FNIRS data is a hemodynamic response. This is oxygenated hemoglobin across time. And we basically use this information. We create Pearson correlation maps to look at connectivity between different regions of the brain. So the regions of the brain were the prefrontal cortex, the supplementary motor area, and the premotor cortex. These are the three regions that are implicated in both cognitive as well as motor planning tasks and have been previously shown to get activated in rehab studies where people were using exoskeletons. So we chose those regions. We conducted functional connectivity analysis, which is looking at the significant correlations between different brain regions. And then we conducted effective connectivity analysis, which is essentially we wanted to extract networks of causal influences of one neural element, in this case, one region of interest, over a second region of interest. So we wanted to know if in a time-dependent format, if one region of the brain regulated changes in another region of the brain that may not have been anatomically connected to each other. So here are some of the results for the study. Let me unpack this for you. So this is functional connectivity data, which is how functionally connected, these are just correlation values that have been transformed between the different brain regions when participants were lifting without the exo and with the exo. And the difference over here are significant. What these are telling us is that there was a significant greater strength between the premotor cortex and the supplementary motor cortex in the exoskeleton condition compared to the control condition. Interestingly, there was also an increased strength, connectivity strength, between the prefrontal cortex, left and medial, with the premotor cortex and the supplementary motor cortex. The supplementary motor area and the premotor cortex are important regulators of postural stabilization and motor planning. And the fact that our prefrontal cortex, which is highly regulates cognitive activities, was significantly connected to these motor regions tell us something about how exoskeletons are potentially imposing mental resources that are needed to get activated in order to do the same physical task without the benefit of reducing loads on the spine, right? And these have implications for safety. Why? Because the prefrontal cortex is the seat of major decision making, being alert, being vigilant. PFC, the prefrontal cortex, is associated with alertness. So if the PFC is engaged otherwise in exoskeleton interaction, it may not have sufficient neural resources to remain alert in the shop floor when they have to look for, moving objects, forklifts, and whatnot. PFC is also associated for concentration and organization. It is associated with decision making and associated with inhibitory control. So not acting when you're not supposed to, as well as self-regulation. So you can imagine if the PFC is engaged in sort of trying to work with the exoskeleton and it's engaged otherwise, the worker may be at a greater risk of maybe, cognitive impairments due to, environmental stressors in their job. Beyond functional connectivity, we also looked at information flow during HEI using effective connectivity. Here we use the Granger causality, which is essentially talking about a time point in one ROI predicts how a second ROI functions in the next time period. And here are some of the significant effective connectivity networks that were formed. We found that in the control condition compared to the exoskeleton condition, in the first 15 minutes of lifting, there were a lot of sort of causal pathways that were created in the exoskeleton condition, but we didn't see as many in the control condition. Now, what we found was that a lot of information was going from the SMA, which is this point over here, to the medial PFC. So SMA was regulating the medial PFC. Now, in motor learning, we have this concept of action monitoring and error processing system. SMA is critical to action monitoring. It's looking at motor action and is identifying whether that action is going as expected. And medial PFC has been implicated in prior motor learning research. When people are making mistakes, the medial PFC acts up. And so we were able to capture this causal pathways that is grounded in theoretical, motor learning basis. So we were really excited to have found this using, effective connectivity analysis and FNIRS during a lifting task. So we found this causal pathway, basically saying that in the early phases of exoskeleton interaction, when participants were lifting, they were probably not moving, their lifting kinematics was not as expected. And that's why the SMA flared up. And they were sort of correcting their motion based on the expectation. And that's why the medial PFC flared up. However, over time, we saw this loop to have disengaged. What this potentially means, and we are working on further understanding and proving this theory, is that there is sort of motor adaptation happens after some time. So of course, with any new technology, humans take a little bit of time, and we were able to capture that. So this was really exciting to us. What we want to do right now with this data is we are trying to come up with various metrics, one for research and other for practice. For research, we are doing a large study in the lab where we have 3 different exoskeleton models. We have a large cohort of people who are going through 5 days of exoskeleton training, one after the other. There'll be different groups for different exoskeleton models, and we'll be doing the same analysis to see whether we see this over days as well. In other ways, neuroergonomics can transform human exoskeleton interaction by establishing the cost of performance, which is we can look at what is the gain on reducing spinal load to the engagement of added cognitive resources, and whether that is an effective trade-off, if you may. And we're trying to work with industries such as Boeing to come up with a good metric that exoskeleton developers as well as industry members can have so that they can rate different exoskeletons and people's adaptation to different exoskeletons over time. With this data, because we can look at motor adaptation, we can look at training strategies. And that is another grant that we are working on that looks at developing a mixed reality platform for exoskeleton training. And we'll talk about that a bit later. I'm part of the ASCM subcommittee on human factors and ergonomics, where we are developing standards and guidelines for exoskeleton evaluation, for system training, usability, identifying and assessing ergonomic risks and cognitive, risk factors and whatnot. So I'm wondering if anyone has any questions. I'm sorry about the OSU dialogue over there, but thank you. If there aren't any questions, I would like to tell you what else is going on in the Neuroergonomics Lab, and I'd be happy to take any questions after that. We have a lot of different work, a lot of different projects going on in the domain of human technology interaction. So we are wanting to expand, this whole neuroergonomic fit framework to look at human technology partnerships for future of work. So far, we have been able to look into human-robot trust. Well, there's a slide on that where we are looking at how do you calibrate trust in automation across different domains. So we are looking at collaborative robots, and now we are also looking at automated vehicles. And finally, much of this work has been focused on cross-university and industry collaborations. But it couldn't happen without them. So this is an example of a project. Very quickly, I will talk about that we have in collaboration with Clemson and Montana State across the computer science, industrial engineering, and IO psychology groups, where we are looking at human-robot collaboration and trust calibration, where my job is to look at regions of the brain to identify when trust is high or low. So we are trying to develop correlates of trust in a way to sort of come up with a more objective correlate of trust that can be deployed in real time to ensure that we make sure that the humans is not over trusting or under trusting in the robotic capability. So we sort of did a study where we fatigued individuals because we wanted to know if fatigued individuals trusted robots more than when they weren't fatigued, because that would be a case of overtrust under impaired operating states. And we did find that neural signatures have strong potential right now for us to calibrate trust in robotics. We are also extending that to looking at cyber threats via HRI trust markers. And so we are simulating cyber threats-based robot perturbations such as harm, sabotage, and steal, so that we can develop hazard response models to detect cyber threats. So the idea is that we'll be using robot data streams to detect cyber threats. We'll be using separate human data streams to detect cyber threats. But our idea is that a combined human and robot data streams can help us identify, trust changes due to the cyber threats. So this is a study that we are in the infancy of, so we don't have a lot of information, but you can see over here, we have multimodal assessments of the brain, as well as eye tracking, and a lot of, physiological responses to look at changes in human-robot interactions. The other project that we have is funded by NSF, the NSF Convergence Accelerator. We are on phase 2 of our Convergence Accelerator, where we are looking at developing a mixed reality learning environment for next-gen emergency responders to use exoskeletons to augment the physical capabilities and augmented reality to augment the cognitive capabilities during operations. So we are working with a lot of different groups across the country, a lot of industry members, a lot of emergency response stakeholders, where we have, people who are roboticists, people who are, in the AR, MR, VR domain, and personalized learning and adaptation to create this training system for emergency responders. Here are some videos of that. I'm going to keep going. So the idea is that we want to develop a training platform that is personalized. Right now, if trainings are not personalized in emergency response, and we want to make that happen. So we are using a human-centered machine learning approach to understand how instructors teach, courses on triage and patient handling to EMS providers, and how do we sort of digitize and quantify it in our machine learning templates so that we can use that for adaptive frameworks. We want this learner platform to be modular for emerging tech. So right now we are looking at exoskeletons and augmented reality. We are also going to be looking at ground robots in the next couple of years. We want the system to be accessible. So that's one of these key points of our project, is that we want to deliver, let's say, teaching triage to an EMS provider via a computer, via a VR headset, via an AR headset, and then using in a regional training facility using augmented reality. So we are trying to work with emergency responders to see what access means to them. Does access mean monetary, constraints? Does it have to be computing constraints? So those are some of the things that we are working on. And we are also working to see if we can scale these trainings to other domains, like industry domains like Boeing and Ford. So we have a lot of different folks. This is a collaboration with Virginia Tech and University of Florida in their ISE, mechanical engineering and civil departments, EHR in education and human resources at A&M. We are collaborating with Peace, Sarcos Robotics, FEMA. So it's an amazing project. It's clearly a challenging and a very interesting, unique experience that we are having as members of this project. I want to end with this very new thing that we are trying to do in our lab, which is we know that emergency responders get fatigued. Now, as we can keep talking about, let's develop a user interface for them that is easy for them, or let's give them enough rest. But really what emergency responders end up doing is they end up taking caffeine, or they end up taking performance enhancement drug, unfortunately, right before an emergency, right as soon as they hear about an emergency, because they don't want to have their fatigue impact their performance or the safety of the team or the public. So what we are trying to do is using non-invasive neurotechnology, a closed loop neurotechnology, which is neurostimulation. We want to send in very weak currents into the brain in a very wearable fashion, such that we can elevate their cognition for at least the time that they are in the emergency. And we've done a lab study, a randomized control trial, where we actually found 1 milliampere direct current for 10 minutes to a person can preserve their performance on a difficult task for 30 minutes beyond that stimulation. Whereas when you don't give that stimulation, that performance declines significantly. We also found that this neurostimulation method helps preserve mood of the person. Whereas, if an emergency responder takes caffeine, caffeine has shown to have both immediate as well as long-term side effects, both in terms of cardiovascular as well as mental health. So hopefully with this, we are going somewhere. I just don't want to talk too much about it, but I'll be happy to answer any questions you have on it. With this, I would like to open the floor for discussion. Thank you.
Thank you very much, Dr. Mehta, for this very insightful talk and letting us appreciate the neural underpinnings of a human technology interaction and how that can be harnessed to improve these interactions as well. So I think this is a very good time to ask questions. If there are any questions, you can either type it for me in the chat for me to read out, or you can just chime in and ask a question.
So just a general question on that large project that you are working on with multiple universities.
Yes.
Can you go back to that slide? Yeah, thank you. So what aspect are you in the Texas A&M working on, or is it just kind of across the board and everybody's doing
Yeah, so no, that's a great point. It's a convergent accelerator project. So we all have different focuses over here. So for example, Virginia Tech is focusing on the human augmentation technology. So they are focusing on technologies that can augment physical capability. So there's a group that does exoskeleton research, and there is a group that does augmented reality research. So they are focusing on that. The folks from University of Florida are focusing on developing VR models of the training. My lab focuses on learning. So how do people learn under these systems, and how can we evaluate them? So my aim, I'm the PI of the project, and we have been trying to, there is no one activity that I can do alone. So at any given point, I have to work with folks from Virginia Tech or folks from University of Florida, as well as people from TEACS. I don't know if you know, Texas A&M has a disaster city and an engineering extension services. It's a huge training facility that trains about 180,000 emergency responders every year. So they are also part of our project. And so they are writing the training for us in terms of, because we can't write a triage course. So they are writing it for us because they're trained to their instructors, and we are sort of converting all of that into a mixed reality platform and doing the evaluations of those.
Yeah, that's pretty impressive. Just managing itself, such a large project must be a huge responsibility, let alone the research, right?
Yeah, I took faculty development leave for that. So hopefully I'm able to manage it. It is a big project, it's different actually. With NSF, it's a cooperative agreement. And so it's not even a grant, it's a cooperative agreement. So we meet with our NSF program director every week on this.
My earlier comment on Ohio State was they always say that they are the Ohio State. And so actually
that's true.
That we are the OSU. Thank you. Great talk. I enjoyed it. It's not my area of research, but it was fascinating to see there's so much work going on in this field, that's relevant, I guess, for, the emergency operators and just a variety of different areas. Thank you.
Yes. Thank you.
So while we wait for questions, I have a couple of questions, but
Of course you do, Joseph. Go ahead.
Yeah, so the first relates to the exoskeleton. And so I realized you had 12 participants, which of course I know you always want to look at the gender effects as well. So you kind of balanced it, yes. So could it be that the number of participants was not enough to have seen the kind of significance you wanted with respect to the compressive force on the spine? Because you kind of do not see any significance with respect to that. Could that be the reason for that?
So that was the first thing I asked our collaborators at the Ohio State University, and they said that the effect sizes are similar to what they have also seen. The things that I did not mention over here is most of the exoskeletons are designed for sagittal lifting, which is you're lifting in this plane.
Oh,
right?
Okay.
If you look at Amazon workers or workers at a warehouse, they're always doing asymmetrical lifting.
Yeah.
Right. And so, yes, if we did a sagittal lifting, we would have probably found some benefits. But we did asymmetrical because that was another question we wanted to get answered, which is, does exoskeleton help, asymmetrical lifting? And we didn't find it. So part of our results could be because it was an asymmetrical lift and the design of the exoskeleton doesn't account for it. But that is the sad reality, right? So everyone went through the same asymmetrical lift. And we have 6 exoskeletons in our lab right now, 2 back and 3 shoulder. And when we asked the vendors, what sort of testing has been done on these? And they said, well, we have done testing in the sagittal plane, and that's about it. And that's a testing for sort of like 30 minutes. And so when I asked them the questions, but that workers, when they wear it, 8 hours a day, and they wear it every day of their working life, how would that change? And then so they said, well, that's why you're doing the research. But what is happening is the research is not caught up. But the adoption of this technology in the workplace has been crazy. Companies are looking for ways to tell their workers to keep lifting And it's not being used as a personal protective equipment anymore. It's being used sort of as an augmentation tool, so there are some ethical challenges with it as well, which I don't think our community is having yet, but I think we need to soon.
Okay, thank you. So again, I'm looking at the chat, there are no questions, so I guess I can ask my other questions. So the other one borders on trusts. So it's something I was interested, I became interested in some time ago, and still I'm interested in, but what I found quite intriguing is the fact that it's a construct, right? So trust is a construct, and so the neural correlates of it is somewhat elusive, I think, sometimes in the research domain. So how are you guys trying to pin that down and know that you're actually measuring trust because of whatever you're doing and not some other thing?
Yeah, no, that's a great question, Joseph, and I'm glad you said, how are you trying to versus how are you doing this? Because we are all trying to, right? I don't know whether it'll end up in something accurate, but we are not assuming that we are going to get a trust outcome, right?
Okay.
So the idea is that we are going to see what's happening in the brain as we change the reliability of the robot. Now, trust can be manipulated through a lot of different things.
Mm-hmm.
So in one of our projects, we are manipulating the reliability of the robot.
Okay.
On a particular task, which was a surface finishing task. We have understood the regions of the brain that have shown up under low reliability versus high, and now we are doing another task in a completely different, assembly and pick up. So collaborative robot is sort of giving us parts in a particular order, and the human is doing the assembly of it, and we are going to create unreliable, scenarios there as well. So what we are hoping is across these very different applications that may have different workload or different sort of cognitive requirements, there might be a common construct that emerges, which is in the unreliable conditions across all of these different conditions and tasks, we find that there are certain regions that are responsible for regulating how another region works. And that is where, I think effective connectivity and graph theory has helped us. And so we are exploring that. We don't know whether it will be successful, but like I said, 3 of my students are OR students, and they're teaching me how to go about doing that. What we are also doing is we are also simulating it in a completely different application, which is driving. So we recently got a grant where we are looking at trust in automated vehicles. And so we are going to make sure that our probe, the brain regions sort of match up. They may not be accurate, but they sort of match up. And we are going to shake trust there as well. So during takeover, we're going to make the AV, the feature not work, and see how the correlates during that time point change. And I'm hoping that we can sort of see some commonalities and deviations of how trust manifests itself into activation across different brain regions.
Okay, thank you. So if there's no other question, again, I'm still waiting. I can ask my last question, right? Sometimes, again, I don't want to take over the show, but I got so excited when I saw your work on neurostimulation, because one of my research framework was the SAA framework, which they call the sense, assess, and augment. And so much of the research has been in sensing and assessing, but augmentation bit is off. So you know that somebody, for example, is fatigued or otherwise, you're looking for ways to help the person or the worker out of it. And so you spoke about first responders, for example, taking caffeine to help them in their task. So with the transcranial direct current stimulation, that's what you're using. I don't know, are there any ethical issues to that, or it's okay because again you are injecting some kind of direct current into a person's brain, as it were, to make them.
I'm sure there are ethical issues that we will need to consider, and so every proposal that we have written, there has been a section on ethical considerations, and so there are guidelines right now in the clinical domain that can help us, and TDCS has been used in military as well, particularly for sleep deprivation. and they have looked at ethical concerns. Now, I don't think, I personally don't think that that such sort of neuro augmentation or neuro enhancement should be taken to private industry. So we have to draw the line somewhere. But where you have sort of public safety, where emergency responders are sort of the unglorified military workforce, right? They don't get the they have all sorts of responsibilities without the right resources. And we at A&M have been too close to them and have worked too closely with them to know all of these issues. And in fact, at one of the conferences, one of the emergency responders came to me and said, are you making some sort of performance enhancement drug that is not going to have me gain weight? Because I will take it in a second. That's how much they need augmentation. And we've talked to them about, these garments that can assess their heart rate variability and all of that. And they said, well, they are really cool. And when we go to expos, they're really cool, but will they work when I'm out, when I'm fighting fire? So neurostimulation is just a technique, right? But how it needs to be implemented is something that I think a human-centered analysis would help. Like I'm not saying that we take the neurostimulation device and a hard hat out in the field when they're fighting fires. I'm saying before they get deployed, when they know that there is an emergency, we need to sort of have a decision support tool that tells us that this person is a candidate for neurostimulation. And then more research needs to be done to see whether the person actually takes it or not. So if it's choice-based. So a lot of research opportunities here. So if you're interested, this is a wide space, and I've gotten a huge positive response from emergency responders.
Sure. I mean, I say that because I also had a chance to look at neurofeedback when I was at Chapel Hill, and we're looking at using that for burnout for physicians. But one of the problems was the long-term effect, because it has some kind of short-term, you can see that, but the long-term, how do you look at it?
Yeah.
It's nothing. But I think we can talk about this later, not now. Yeah.
No problem.
Okay, thank you. I don't see any questions, at least not from my end. I still have some time. If you have any questions, please ask.
Yeah, and I think, Ranjana, you probably know this already, but we just made our the last two hires that we made were.
Oh, I think you went on mute.
Okay, sorry, I touched a button here on the keypad. Yeah, what I was saying was that it was only in the last year that we hired 2 human factors faculty, and until then we really had, we had Tim Harden who teaches, but he doesn't do research. So we are now trying to ramp up that core area, and so the graduate students that have joined, there's really only one that is now beginning to work in this field, which is probably why you have more questions from Joseph than others.
No problem. I completely understand, and I'm so glad that you guys have 2 human factors people. I was talking to someone at NSF, and they said, human at the center of systems is something that they are very human. In the loop systems is something that NSF is very interested in, and one of the 10 NSF big ideas is on future of work that has humans, completely, embedded in. So I think there's for human factors faculty, it's the funding, looks good from NSF point of view. So there are a lot of opportunities for sure.
So how big is the human factors group at Texas A&M?
We just had our graduate academic program review last week, so I know it. We are 7 faculty in human factors, and we call ourselves health and human systems engineering people. So we have 1 full professor who does biomechanics research. We have 2 associate professors, me and Tom Ferris, and then we have 3 assistant professors, Farzan, Tony McDonald, and Mariam Zahabi. We have a professor of practice, human factors professor of practice. And then Mark Lawley we call him a human factors guy, because he's doing a lot more human factors research right now than he used to before.
Okay, so you've got a pretty sizable footprint in that area.
Yeah, and this is in the last, I think, 4 years. So I was hired only 3 years back. So we are one of the new hires of the department.
Okay.
Okay, so I think it's 3:30 now. So on behalf of the department, I want to say a very big thank you to Dr. Mehta for this very insightful presentation. And of course, we will have this recorded as well, so anyone can watch it after the fact. Thank you, and have a very good rest of your day.
Thank you, everyone.
Thank you again. Appreciate it a lot.
Bye.